Hi, in this video I'm going to talk about what is seemingly unrelated regression, in short known as SUR or SURE. Okay, so it's about a system of linear regression where we jointly estimate multiple models. So if there are more than one linear regression model, we can estimate jointly, and that's called SUR or seemingly unrelated regression. It's useful sometimes. You might wonder why we need to jointly estimate when we can separately estimate the models. But sometimes it's useful, and we'll take an example to see that. So it's mostly about a single model containing a number of linear equations, and then we basically estimate at the same time without having to estimate separately, right? And the assumption here is that the error terms are correlated, and many times the error terms between different linear regression models are correlated, and that's when SUR is quite helpful. But in case they are not related, the error terms are not correlated, then there is no much advantage of using SUR over separately building linear regression model. You can also relate it to simultaneous equation models when you have endogenous variables become exogenous variable and exogenous variables becoming endogenous variable. So that's also a special case of SUR, and SUR is basically a special case of generalized linear model. So without having to sort of get into the details of why it is a special case, I will try to keep it very focused on what SUR is and where it is used and how we can perform it. And it's not always useful, by the way. It's useful only in a limited very limited problems, and we'll see what kind of problems where it is useful. But the bottom line here is that we are trying to estimate parameters of multiple models at the same time. So we'll take an example. First we'll install the packages. The most important package is the system fit. So this is the package that is going to be used for SUR, but there are some dependencies, so we have to also install some of the other packages such as foreign, car, MGCV, such that. Okay, now I've already installed, but you can install. So these packages are the most important packages before we can run system fit. Okay, we'll take a data set where we can perform linear regression model. As I told you, it's all about linear regression model, but more than one linear regression model. So we'll first upload the data, and let's first see how the data looks like. The data is about is education data taken from some universities, where you have scores from different areas, academic areas such as mathematics, reading, writing scores, and then you have program, socioeconomic status of the student, race, gender, whether it's female or male. Okay, and we like to build some linear regression model as to how someone's math score is related to his or her socioeconomic status, his race, gender, program type, so on and so forth. Okay, similarly, how someone's math writing ability is related to some of these factors. So we then build two system of equations. One is reading ability with respect to female, as in female yes or no. Okay, so that's gender, and then you have socioeconomic status, and then you have social studies marks, and then mathematical ability depending. So that's basically your left hand variable, which is the endogenous or dependent variable, and exogenous variables are female, and then socioeconomic status and score in science. Okay, so there are two sets of linear regression model, but you can even have more than two, need not be only two. Okay, and then instead of the LM function that we normally use for OLS regression model in R, we will be using system fit, which will fit regression coefficient, will find the regression coefficient simultaneously without having to do it separately for these two equations. Okay, so this is something we give, so you can give any name. This function system fit is used here, and then we have to use the list function here, because it's more than one. So it's about, yeah, here is the um, score is stored here. Basically R is taken from R1 here, so it's this equation and this is the second equation. Okay, and you provide the data set and we summarize it. Okay, let's run this. So simple syntax, right? Just a difference of combining these two equations, nothing more than that. All right, now we see the system of equations and the parameters that we have got. So I'm going to show you how it looks like. Okay, it starts with separately as to how many observations, the sum of square, R square, and so on. R square 40% for the first equation, where we see a reading ability, and for the second equation it's 41%, which is about the mathematical ability. Here covariance matrix is used, which is very unlikely to unlike the OLS regression. Not getting into the details of it, why it is used, but something to do with the error being correlated between these two regression models. Okay, and that's the theoretical aspect of how the estimation process is in this kind of estimation. Okay, and then you have separately you have values for these two equations. Okay, so you have for reading ability, this is the equation and these are the estimates. You have intercepts and you have slope coefficients as well, like you have in any other OLS regression. So the output looks pretty similar to how you get from a normal OLS regression model. And you have t values and p values for you to assess if the model is, if the parameter is significant or not. All right, so all that is given for the first equation, and then we have for the second equation, which is about someone's maths ability or ability to do well in maths. And we have three exogenous variables. One of them is common, which is the female, the other two not. Well, yeah, two variables are common, right, in equations, but you can also have all three or all of the exogenous variables common, but in that case SUR is not very useful. Okay, it's useful only when you have at least one of the independent variables different in these equations. There must be some level of difference there. Okay, all right, so now we have got it, but where is it used, right? So here is an example of where we use it in research. Well, this is an example. We like to see in the same system of equation, we like to see the impact of female gender on these two scores, whether we have a difference in these two regression models, right? So for that we will use a new package called CAR, and we'll try to put a restriction that the estimate of the variable, independent variable female, should be the same in both equation. Now that's our null hypothesis. It could also be different, right? And then use a linear hypothesis function and provide parameters such as the fit SUR, which is based nothing but the name of the estimates where it is stored, right? Here we use fit SUR, just we can use any name basically here. And then we put a restriction, and what the restriction is that the female parameter of the independent variable female should be exactly same, and we do a chi-square test on that. This is a hypothesis test just to see if there is a difference. And remember, the other two independent variables are unchanged. We don't make any changes in them. We control them and see if there is some sort of an difference in the impact because of someone's gender. Okay. Now here you see the p-value is greater than 0.05. So basically we do not reject the null hypothesis in that case. That means we accept the null hypothesis, which is that the impact of female is the same, right? There is hardly any statistical difference of someone's gender on score on maths and reading ability. Okay, so that's one example or one use of this type of estimation. Of course, you can do it separately also, but this is more convenient when you see some sort of a correlation between the errors